And away we go. Okay, so we did
So if there's anything today I can't do it, I have to leave it. Either 11:50 or 10:50.
Okay, so there's some. Super. So I got my folks this morning. Good morning, Kiara and Lauren. Good morning, Malta and Amelie and Linus. Thanks all of you for joining us. 3 more and we got her late. Good. So what we're going to do today is 2 things, folks. We're going to compare, and again, you may want to move Jake behind him just permanently for me. Otherwise, it's so hard to see. To compare TV effect with generator effect, which part of you haven't seen yet. Then start electromagnetic lab, which we'll do together. Okay, what was the effect called yesterday? Essentially called yesterday. Tim, thank you. You are wide awake this morning. That's great. So the motor effect, right? And essentially, good. Thank you. Kiara had that as well. Super. So I'm glad you guys can hear and see okay. Anybody else there? Just say hello so I know who else is present. But I think I got most of you. And today's the 11th of May. Right. You know what? I'm going to review this with people at home, and I'm going to show this to all the rest of you here for the first time. Okay? So, folks at home, be ready to tell me what's going on. What I've got now is a really big voltmeter. You might have used a voltmeter in 8th grade. Not this big, the smaller one. Do you remember measuring voltage, any of you last year? Yeah, you did English? Okay, some of you did. I'm going to put this here just so I get a little more room. Let me know if it's in your way. It is going to be in your way. Well, okay, so I'll move it out of your way when we get set up here. Okay. So I can stuff on here. My deal is, you know what I can do is get all these pens out of the way. That's not mine anyway. Oops. Let's open a couple windows. Let's see. Can you get the one back there? It's certainly warm enough anyway. Good. I'll change my line. Move back here. And way back so everybody can see it, including folks at home. There, by golly. Okay, finally I can get it. Okay, so folks at home have seen this. What I'm going to do is I've got this on millivolts. Is that a big or small amount of volts? Millivolts. What do you think, just from its name, Corey? Yeah, small, right? It's a thousandth of a volt, so it's not a lot of voltage. And I got just one lead, so I'm going to do something funny. I'm going to take it and put it in and just make one circle with itself. I'm not plugged into any sort of electricity source, so it doesn't involve a power source. Now, whoops, I got somebody else with us. I got several somebody. So let me write who else I got. I got Charlotte and good. And I got Timothy P. And let me write you two down. Huge. And I got a really big magnet. So I'm going to put this loop over. It's not plugged in. And yet, what am I making happen in the lead? Don't let your eyes fool you. This really does tell you. Bless you.
You're reading a magnetic field
Yeah.
by breaking the other, and the voltage is like that.
Yeah. So what does that mean is happening in the wire, in the lead? What must be going on in here, even though I can't see it? Clara.
You're like pushing away.
Yeah, what's being pushed in there? The electrons, super. And once they start pushing and moving, we say that not only do I have voltage, but I have what other thing with electricity? What do I have that's called when the electrons are moving? We say we have what? We say we have what, Tim? Current. We got electric current. This, folks, is a way to make electricity. It's the way our society essentially makes electricity, but it is a way to do it. Okay. Now, I'm going to read comments at home. You got it. So, Kiara points out that I got to have enough momentum to do this. Watch if I go, okay, here I go normal speed, right? Watch if I go really fast or really slow. Doesn't do much, does it? So to make a fair amount of electricity, it also depends on the of the loop. So what am I varying, Corey? The speed. So it depends on the speed or velocity of the loop. And folks at home, what else does it depend on? What else did you see? So not just the speed of the loop, but what else? And while they're answering that, I want everybody here to notice something else. When I put it down, check out the lever very carefully on the voltmeter. What happens when I go down versus when I go up? What happens to the lever? Yeah.
When you go down, it only has a TNT movement at the very bottom.
Yeah.
But then when you go back up, it like pulls up and then you pull it.
Yeah. Not only that, Liam, but when I go down, it actually runs out of room. It goes onto the side a little bit. If you can see that, Stella, or not. It goes onto the side, the negative side. So I got negative side and I got then positive side, like Liam said, when it comes up. Okay, so how can I make more current? What can I do, folks at home? I got one person has it. Let's see if others at home remember. What can I change about the situation? So I can certainly make it faster. That helps some. And Kiara has it. Let's see if someone else knows there too. I think we'll just go and well, let's do that. Okay, so I'm going to do it normal, Tim. Bum, bum. And now I'm going to turn it. Bum, bum. Ah, so when I turn the loop around, if you think about it, it kind of makes sense. Because what happens then, Zach?
When you go down, the bar goes higher, but then when you go back up.
Yeah, it goes voltage, right? Voltage gets higher, and when I pull up, it gets negative. So it's the opposite of when I do that, right? Now, pretend all of you are like electrons in a wire. And the good thing that Clara said earlier is pushed. When I stick you in a magnetic field, you're pushed one way or the other. And that depends, the direction depends on if your voltage is negative or positive, that back and forth business, okay? We say your direction is alternating. You ever heard that word alternating in terms of electricity? Alternating current. What's a shorthand for alternating current?
Does it find its own way?
Yeah, no, the shorthand, AC. AC. That's what we use at home, alternating current. We're gonna see how that works coming from the power plant in Berlin to your house. Yeah,
So what's like AC/DC?
yep, that's where the band AC/DC comes from. AC is alternating current. What's the D stand for in DC? You know?
Divergent.
No, close, direct. Direct current. We'll see what that is later on. Okay, let's see who else answered. Yeah, so Charlotte knew as well as Kiara and Lauren, more loops. And Amelie said this as well. Here we go. So what do they mean by that? Well, check this out. So here we go. Bum, bum. What if I make two loops? Whoa. Well, let's see it.
So whenever you put it down, the voltage became way higher than when you had one.
Yeah,
Not only that, when you put it down, when it had one, the voltage was the negative sign once it reached the bottom, but now it's at the positive side.
well, it's still at the negative side. I just can't go over there.
Yeah.
Yeah, so, but it still goes up on the positive side. I'm gonna do 3 now. Alessia, let's see what that looks like. Whoa, I've topped out, haven't I? And actually, there's a direct relationship here if I measured it carefully. The more loops, the more, what could I say? The more loops, the more, maybe there's more than one word you could put in there, Ingrid? Yeah, more loops, more electrical current. Good, multiple loops. Yeah, thanks everybody at home. That's right, Kiara had it as well. Dynamite, good. This is called the generator effect. And you can probably guess it comes from an electric generator, right? Sometimes you can buy these at home. I don't know if anybody has one or had family in the States who might have one. Anybody got an electric generator at home?
Not here, but we're still in.
Yeah. And it's in case there's what, Corey? Why do people buy them?
Well, when the electricity is out, so they open it, it's for some.
Exactly, good. When the electricity is out, my brother bought one. He lives in Oregon in the US. And if electricity goes out, he has a diesel engine, he has some diesel fuel in there. And when that runs, it makes something go up and down in a magnetic field. And for the house, they produce their own electric current, right? Produce their own electric current. Not quite like this, but you're going to see how it would look later on in the course. So this is the generator effect. Now, let's look at some angles. I know that sounds like math or geometry, but here's what I mean. What angle am I doing compared to, here's the field, right? The magnetic field goes from north to south, so it's like this way. What angle am I going and meeting that field with as I go down? That's essentially what angle here. It's nothing supposed to be tricky, Zach. 90 degrees, good. Now, so I got magnetic field, direction of my force, right? I'm going down 90 degrees. And now here's another angle. My force is going this way, but the wire's like this. And here we said the electrons were probably doing, Clara, what again? Yeah, I mean, so they're going what? This way or this way, right? Measure me that angle. So that compared to the angle here of me pushing my loop down through here. So well, that's also what? 90 degrees. So you ready? Huh? And huh? I'm gonna make it so these others can see it. So bum and bum, that's 90 degrees, right? And 90. And 90. Down and this way. Eventually in math class, you're gonna have what's called, you've had the X and the Y axis, right?
Yeah.
And they're 90 degrees, right?
Yeah.
Well, next year you're gonna get X, Y, and Z. And Z is kind of like this. Here's X and Y. Can you guess which Z goes? So there'd be X and there's Y. Which way would Z go? Or it goes up. Why do I need three axes? Not just for physics, but in general. What is it about life? Why do you suppose you really need three axes for a lot of things? So, 3D. Life is three-dimensional, isn't it? And now you know something physics-wise that's also three-dimensional, and so does everybody at home. So we need three dimensions, X, Y, and Z, because we've got three directions here. The field is this way. The electrons are moving either this way or the other way. So that's at 90. And then my movement is another 90 degrees. And we're going to sketch that right now. Okay? So I'm going to put this down for a second. Because what we're doing, bear with me, all right? What we're doing is we're trying to compare. Let me turn so these out. Okay. I don't want to get this big magnet near my laptop, do I? You ever hear that? Yeah, it screws up your laptop because of some electromagnetic effects that you don't want. So for future efforts. Okay, so comparing generator effect to motor effect. So let's say for the generator, I have my wire going like this direction. Oh, that's a terrible wire. Let's try that again. That's probably the worst lead I've ever drawn in my life. Let's just draw one to make it simple. So the electrons are either going this way or this way in the wire. Then I got a big magnet. I draw it like that. It's not quite perfect, but north, south. And we learned yesterday that a direction of a field goes like this, north to south. And I'm going to label that first. So north to south in magnetic field. I put a little arrow here too. I know I'm going to have a lot of little arrows. I'm sorry about that. Just the way life's got to be. Because there's three things happening here, right? The electric or the magnetic field I can't see, but it's going essentially this way, north to south. The electrons, we make them move, and I showed that with my little red arrows. So I'll write the arrows are electrons moving, and that's also called electric current. And then finally, we got this going. So that's the loop of wire. And by the way, it's also called a coil or a lead, moving up and down. that's actually not bad this year. That's kind of how I want you to see it. Let's see if folks at home can see it easier. And thanks, yeah, 90 degrees is exactly right. Diagram, especially because I don't usually draw it that well. Sorry. Okay. See, that's one of my better drawings. Not bad at all. Okay, so I got some 90-degree angles, don't I? Essentially, I got these look like they're parallel, they're not. This is really 90 degrees here. And this is 90 degrees. So, magnetic field is, what's the word for 90 degrees in math? Not the word, sorry, the symbol for 90 degrees in math. Have you had that? What's that look like, Liam?
Like the square on the edge of kind of a ball.
Good, that's what we're gonna draw. Thank you, Liam. So it's called perpendicular, isn't it? And you all know what that means, right? Because you had that in math. Yes, yes, I hope. Okay, so the magnetic field is perpendicular to the let's make sure I got it right. Is perpendicular, yeah, to the movement of this, isn't it? To the movement of the loop. And the loop movement is perpendicular to the electrons flowing, or electrons movement. That's the one in the red, right? And the magnetic field is also perpendicular to that. So what I'm trying to say is, I got three right angles here. Perpendicular, perpendicular, perpendicular in the generator, okay? All right, I'm gonna pause and see if folks at home have questions on that. So I got maybe I should number these, right? 1, 2, 3. Okay, so I got the magnetic field is perpendicular to the movement of the loop. So, yep, that's right. I got the loop movement is perpendicular to the electrons. So I move the loop, but the electrons go this way. So that's 90 degrees. And then I got the magnetic field is perpendicular to the electrons movement as well. The electrons are going in the wire this way, and I got to break the field coming down through it like that. Or sorry, that's the field. And I got to have the electrons going this way. Yeah, so all three are perpendicular. Crazy. I know it's early in the morning. It's a lot of physics for early in the morning. Let's see. How it looked again with the motor. Okay, so that was the generator. Over here, we're going to draw the motor effect. I'm going to erase that because I need space. Bye-bye objective. All right, so all that was about the generator. Let's review the motor now and then draw a picture of that as well. I'm really taking my time with you here because one, it's super important. Two, it's not that easy. I know that. So I know you're waking up, but if you got questions either at home or here, please ask me about this, okay? So that's the motor effect. Let me plug in my 2 extension cords and get some power to the laptop as well. These are complex here in this room. okey-dokey. Power switch 1. We are on. We are on. Yes, Houston, we can do this. As I used to say. As opposed to Houston, we have a problem, which we don't. Okay. All right. I brought a bigger magnet today in hopes you guys can see it easier. A bigger magnet. No, not a bigger magnet. What's this called? It's not a magnet, it's a what? It's a really big Ingrid? Compass. Okay, so you need that too. Yeah, so it's a really big compass. And it's kind of heavy. It may not move as much, but I think from the back of the room, especially like Avram and stuff, might be able to see that easier. The other one's pretty small, huh? Okay, now let's arrange these folks so they can see it too. And remember, this is our power source. So this time I am using what? For the generator, I wasn't using this, but for this time I am using what to make something happen? I am using Claire? Power, electricity, right? Yeah, so I am using it here. So that's different than the generator. For the generator, maybe I should write it here. But the goal, just so we know, the goal is what for a generator? It's used to stop?
Get power.
To get power, to make electricity. So goal, so used to make electricity. It generates electricity. You ever heard that? That word? Okay, so generates. Just said that the goal of the generator is used to make electricity. Yeah, okay, and thank you. Kiara as well. Good. Okay, let's put in that lead. I need a good one here. I'd like a smaller one. Do I have a smaller one? It doesn't matter. The length of this lead does not matter to this at all. Okay, so. Okay, power, check. Folks at home? Yeah, they can kind of see it. Folks at home, here's my compass. And here's my power source, and my hands are probably in your way. And let's crank this thing up. And nothing happens because it's too heavy, isn't it? I'm going to use more amperes, which is more what? Amperes is a measure of what? Remember, Tim? No, voltage is in volts. Amperes is a measure of when? No, that's the same word. Amperes is a measure of what? Let's see.
Current.
Current. Okay, so I'm going to add more current. You ready? Here we go. Turn it up a notch. Now I'm going to crank it up and down like we did yesterday. Whoop, still not much. I'm going to put it on the maximum and try it, okay? Maximum current. And here we go. Oh, come on. I got it to work in the lab. Well, it's not working, period. Well, it looks like it is. Unless I burnt something out, but I don't smell anything burning. I believe so. I can try a different lead, but that shouldn't really matter. You know what? I'm going to just turn this. It shouldn't matter, but let's go ahead and do it. Okay, I'm getting more current in that. Oh, there we go. It's minimal, but you can get it moving a little bit. Everybody see it wavering just a tiny bit? Now I know why I use the other one. This blade is really heavy, so it's taking a lot more to do it. Let's go back and use the other dog on it. Because that's so much easier to see. Okay, sorry about that. Try to do something helpful for you. Okay, so let this thing go to north. So right now my compass is lining up. Who haven't I talked to? Jay. My compass is lining up with the magnetic field right now. What's it lining up with right now? No, it's lining up with the Earth's magnetic field. Okay, so now it's all done doing that. Now I'm going to put the little loop by one part of it and crank it. Oh, and this time it moves so easily because it's a much lighter needle. And let's see if folks at home can see that. And we said if I turn my loop upside down, Abram, what's going to happen? Yeah, it goes, so to speak. So now it went attract, and then attract. And if I turn it upside down, instead of attracting, what's the opposite of that, Abram? Well, not quite. What's the word? What's the word? It's clear. Repel. So there we go. And Abram, you're right. It's pushing it away now when I turn that upside down. Oh man, I can almost do 360. Ow! Okay, I can't because I'm still fighting against the Earth's field too, aren't I? It wants to go back to the Earth's magnetic field when I turn it down. Okay, so let's analyze this. Analyze this. So now let's talk about the motor a little bit. So here's my compass. Motor effect. The compass I got. And then I put a loop here, a wire. This is in my power source. Power source. That plugs in. Hello, quarters. Yeah, this one's actually easier to draw, isn't it? So when I make the electrons move here, then this thing goes like this. This thing goes like this. Or and I know we drew this yesterday, but I'm still going to draw it again for turns. And I flip it around. And then it, as Claire said, it repels. So it goes right. This side. And that's when the electrons go the other way. No, actually, okay, they're it's flipped, so I'm going to show that. It doesn't matter. I'll just say the electrons move the other direction. Okay. So let's talk about this with the research. Some of that. Okay, so the motor effect. As we turn on current, electrons flow in white. Okay. Flowing current creates a new. All right, we had this yesterday, and I think Tim got it yesterday. Let's see if some others can get it today. So when I have the current flowing, I'm creating a new heat in the wire. Current. Thank you. Okay, so this results in, if you think about it, what's a push or a pull probe in physics? Results in a what? A push or a pull. It's called a heat in physics. Let me ask folks at home. So when I got the current moving, I get a push or a pull. What's a push or a pull in physics? Yeah, no, they've been showing up, Kiara. It's okay. Yeah. So push or pull is what in physics? Zach, you got a guess?
Well,
You had it in 8th grade for sure. Push or pull. Push or pull. Starts with an F, times the force.
Force,
Of course. Okay, so
only with you.
so to speak, or with us in this case. Okay, so this results in a force which moves the compass needle. Okay. Yeah, it is attracting and repelling. That is true. Okay, I got somebody I don't know. You better, surfer, you better tell me who you are or I gotta like get rid of you. So, surfer, identify yourself or I'm gonna zap you and get rid of you. All right, you gotta tell me who you are so I can take roll. Okay, so what's going on here? So I got this direction and the force that I get is perpendicular to that. So the force is perpendicular to the magnetic field, isn't it? That's why it makes the little magnet move or the needle move. And the force is also perpendicular to the electric current. So if the electrons are moving here, then the force is going either attracting or repelling, and that's perpendicular as well. Okay, sorry. Got it. Oh, it's Michael. All right. Okay, Michael, no quats, all right? But in the future, tell me who you are so I can take roll. Otherwise, you don't get any credit. Okay. And I'm trying to think of how to say this last part. The last part has to be perpendicular as well, but now I'm thinking about how that's the case. So if I have it like that, I think it just produces a field that's perpendicular. New magnetic field is perpendicular to the old one. And the old one is Earth's, like we said at this point, right? Because that's what the compass needle was originally lined with. So, that having been said, we got 3 right angles in each of these sort of situations. And what I want you to kind of consider is that the motor effect in the generator is, do I have a phone with me? I do. We say in English that's two sides of the same coin. In other words, I know they looked different, but they're both involving these 3 things. I got a force, I got an electrical field, and I got flowing current. So all 3 of those things are in both of these. And what we're going to call these is named after a German scientist, and it's called the Lorentz force, which I'll write in just a second. Get off this so I can see my people again. There we go. Okay, so questions so far? I know that's pretty technical. Some of my German colleagues and Frau Rockais, have you learned this right-hand rule? I find it to be challenging enough for students that I don't bother having to do it. But you can look up on the internet right-hand rule, and you'll see if the current goes one way and the force goes another, then you can kind of do like this and hold your fingers at 3 perpendicular angles. And even if you don't understand the rule, just that, I hope, helps you understand the physics a little better. So I got a 90-degree angle here, and here, and here. So I really do got three 90 degrees if you want to try and make your fingers that way. That's kind of what's happening in both the motor effect and the generator effect with these 3 things. I know, see if you can limber your fingers up like that. First do that, and then sort of fingers straight out like you're pointing forward. And if you can do all that, that's the 3 different qualities we need. I want to say forces, because one is an electrical current, one's a magnetic field, and one is a force. But those are the 3 things we got. I kind of like that. Anyway, so if you just hold that, you can think about it. Huge. So let's make a little space. Good. Okay. We'll talk about the Lorentz force, and I will start our group lab next period. So, folks at home, take a break too for 7 minutes, and then we'll start up. Maybe I'll leave that for a minute. And folks at home, if you got questions, please also ask me. Well, it's not bad. We got a double period, Charlotte. Don't go too far. Be back in 7 minutes, all right? Oh, that's it.
I have an important question. Did you get the email regarding the
Yes.
Yeah,
Are we doing that today?
no, next
No,
week.
next week. Yeah, we're gonna
Yeah,
do that.
so when should we?
Could you be in charge of having to remind me that I'll probably remember it, but can you remind me
Yeah, we
about
can-
it or something?
Yeah, we can do it either Monday, Tuesday, or Wednesday,
Both my eyes,
or Wednesday.
Right.
like,
And of course, we'll only have half the students here. Well, wait a minute,
Well, yeah,
you're not gonna be here. Ah,
Next
sit
week,
there. I'm not
multiple
gonna sit there.
students need the alternate.
can you ask?
Sit there and watch it.
Like in class always.
I'm literally about to pass out.
Don't fall out of the window though.
That'd be really fun.
Yeah.
And I get a presentation and then we'll go.
Or you can do the presentation.
Always
I
meet
think
and then,
like just a brief overview, I'll try
like
to have a
having
slideshow
individual
to classmates.
and I think
Yeah,
so
could you
next
do that
week,
ahead
so
of time?
I'm like,
Because you won't be
wait,
here.
next week, and then I'm like, wait,
It's gonna be a live stream video.
I was like, but like
No,
the
but
board is in
we
the
have
right
like
place.
there's 1
the
week
chairs
for the
in right
A
place
kids
for
and
it.
1 week for the B kids. Yeah,
Okay. And you'll do it in 2 weeks, how's that sound?
yeah,
And hopefully you do it
yeah,
next
I'm
week.
trying to tell this part of the slideshow to the class and make a copy so that they can take a look at it and then I'll just give like a brief overview.
That sounds really good. I'm about to do the same for this.
Mr. Lance, do I just put this here? You still
Hey,
need it?
thank you for that.
I kind of
I do.
figured because my pen was like split.
It's okay, that's perfectly fine. Thank you very much. Good. Any other consent forms you got, hand it to me. And folks at home, if you got consent forms, please take a picture and upload it. Upload it into Google Classroom, and then I have that as well, okay? Let me write down my, where are you? Okay. Good. All right. So again, folks at home, any consent forms, just take a picture, upload it into Google Classroom for me. Thank you.
Really? You want to leave?
No. Oh my God.
You gotta find some for a second. No, no. We have about some for this one.
You something?
Yeah, but it's a family friend. She's a graphic artist. And she has art in like the museum. Yeah, you guys.
Here, of course. Every day, someone. Every day, someone. You don't want to work on it. I'm going to do it. On that friend.
So far, it's about a girl who has telekinetic powers and like magic and stuff. Like a babysitter. Is it like? Yeah. Yeah. So far, yeah. It's yeah. So far, it's interesting.
Anyway, I just sent her my portfolio. And so what? Yeah, but that would mess everything up. So you said next year we're gonna have 10th graders and 10th graders at the same time.
Well, you missed the first hour, so you'll have to watch the first video. So Candace, I don't know who you are. You'll have to tell me what name you are in my class. All right? Candace, identify yourself so I can take roll. But you missed first period, so you'll have to watch the first part of the video and take notes. All right? But tell me who you are.
Any idea if still we have practical this year?
Yeah, but most of the online, I'm guessing. A lot of them, because it's hard to find places to take you. But if you're creative, you can find some places that will do something with you.
Yeah.
But they're still gonna try and have it with you towards the end of June, I think it is.
Yeah, I mean, like, the only thing I could find for COVID, I can, is like 1 week at a bookshop with lunch with my mom's friend.
Why just 1 week?
Because she already has someone.
For another week?
No, no.
Yeah. And I mean, like,
With a slide.
because of COVID, all the places that I applied to, are all here.
No, I
We
mean,
just couldn't do it.
when we have
I
something.
understand.
They had a backup plan, someone who worked on a movie, you know, they first started one of the authors. He worked on a movie and I could have gone, it's impossible to get no
We
problem.
have like this week, we have like next week. Well, not next week, this one. In 2 weeks. And then we have,
Once again, you will not have a semester test for me. They're only gonna have it this year for math, English, and German. I think those three subjects.
Did they cancel that?
No. No, I think you have it those three subjects, but you don't have any for me, so we're doing just quizzes. Quizzes and assignments, Alessia, but that's gonna be it for you and I and participation. Okay. I don't have any sort of date for you, okay? All right, so, and my video is still running, that's good. I'm gonna erase this, because I hope everybody's got it at home too. Okay, so both demos involve the, and I'm gonna spell it right this year too. Lorraine force. So we're gonna define what that is, okay? All right, I Googled several definitions because some were so complicated and I wanted to find one that made sense for you. Well, that was clever of me. I ripped up some of this for pieces. I don't think I want to take time to do that puzzle. One of the smarter things. All right, so we'll just piece it together. Okay, Lorentz force is not surprisingly, an electromagnetic force. Which I hope makes sense because it does. It involves what? Electricity and magnetism. Thanks, Alessia. So obviously that's why they get that name to it. It sounds complicated, but now you've seen that it really is what it is. It's electro and magnetic. It's very blurry. Okay, I will try and read it off to you. Thanks, Malta and Kiara. It says, both demos involve a Lorentz force, and the Lorentz force is an electromagnetic force. You can get that over as far as possible so you can see that writing. Lorentz force is an electromagnetic force, and Lorentz has a Z at the end. force on a charge like an electron. So the charged particle we're talking about is an electron, okay? The force on a charge, like an electron, is a combination of the force in the direction of an electric field. That's like our power source, or the moving electrons, and I'm going to put a little star here. We're going to add something to it later. And a force at a right angle to the magnetic field. The little star is related to the strength of the field, strength of the electric field, and the velocity of the charge. Okay. Now, I want to give you an alternative definition that's maybe a little simpler. Okay, so the first one I wrote, again, also for folks at home. Lorentz force, it's an electromagnetic force. The force on a charge, like an electron, is a combination of the force in the direction of the electric field, that's pushing it along the wire, and a force at a right angle to the magnetic field. And that electrical field is related to the strength of the electric field and the velocity of the charge. So how quickly the current is flowing. Okay, an alternative is that the Lorentz force is the force on a charged particle due to electrical and magnetic fields. Let's see if that helps there. Okay, I don't know who this person is, so they're going to be out of here. Okay, I know that's a lot of writing, and just do some thinking as much as you can. Um, the first one's more complicated, but it's probably more accurate. The second one is sort of like the one we did, which was the generator effect, but it doesn't work so well when we talk about the motor effect. So the alternative is not perfect, even though it's shorter. Oh, darn it, that's really not very right. 12 demos involve one, flowing current, I should ask you, you've seen now enough of this. Okay, so stop, let the students catch up, and then let me have you fill in the other two things over the right. Okay, so same with folks at home. Go ahead and try and draw that in your notes, ask me questions, and then once we caught up, we're going to try and fill in these three. So both demos involve what three things? Certainly flowing current and also two other things. Okay, you got one? Yeah.
Maybe one magnetic field.
Super, good. Magnetic field. Sorry.
Is it force?
Yeah, well done. Really good. If you all understand that those three things are what work in both demos, then I hope you understand that, aha, really generator effect and motor effect are, and I'm going to use my cheesy expression, are two sides of the same coin. So they're similar, even though we get different things out of it. The one we get movement, that's the motor, and the other, instead of getting movement, we get electricity out of it. If we move it, then we get electricity flowing. So we get electric current. Huge. Whew. Okay. Good. Good, and I got one more. Okay, so I'm going to hand all of you out something here. Make sure everybody's sort of done taking notes. Okay, my folks at home, while these guys are taking notes, I want you to find something. Please find this. I sent it to you in the group stream for Google Classroom. And it says, how can we generate electric current? And it's essentially 4 things we're going to do together. And you can either print it or you can look at it back and forth as we do it and then take notes in your notes on it. Okay? So we're going to do these 4 experiments together. 1, 2, 3, 4. Just the way we got to do it because we're not in a lab room. So I can't have my students do it, unfortunately. And I'm going to hand this out to them now, but you can find that in the Google Classroom stream. Okay? Whoa, okay, so you guys, let's give you a question. All right, so we're going to do the first one together. And it kind of looks like this. I've got a big coil a bunch of loop, and then I've got a magnet, and I got this hooked up to a voltmeter. So I'm going to see which one that is over here. I'm going to take my class at home with me. And I brought so much stuff, and I need to put this on a chair. Or not. Maybe I'll move this over and put it back behind. So here's my coil. I'll hold this up for everybody. We used one of those last time with you guys. Yes, yes, no, no. No, you haven't seen that. Okay, so it's got a lot of what? What else do we call that? Coil has a lot of what? Another word we use for us? No, it's not spring. No, then it's not springy. A lot of them loops. A lot of loops of wire, right? So this coil has lots and lots and lots of loops. So you may want to label it on your drawing, coil, right? C-O-I-L, coil. And we got to hook this up to a voltmeter. Now let's see if I got one already. I hope I do. Got a couple coils here. There it is. All right, so I got this hooked up to a voltmeter. And this one's digital. And I'm going to turn it on. And not surprisingly, right now the voltage is 0. There's nothing going on, right? Folks at home can see that too, I hope. So there's no voltage. But there will be. And what I got to do is, let's read experiment number 1. Well, they don't give you a lot on there. Experimental procedure. What do you suppose they want you to do? Look at the picture and the arrows. What do you suppose they want you to do in number 1? What do you suppose the procedure is? Tim, start us off. Okay, good. So we're going to slide the copper coil over the magnet, or there's another arrow, or Stella, or move the copper coil over the magnet. So it looks like that's the 2 things we're going to do, right? Okay, so folks at home, so you can write that as well under A and B. These guys said we're going to move the copper coil over the magnet. I think that was Tim. And then from Stella, we're going to move the magnet into the copper coil. So copper coil move into magnet, and second one B, magnet move into copper coil. Okay, copper coil, we're going to move into the magnet. So I better get the magnet. Here it should be. I hope that's going to work. I don't know if it's going to fit. Is it going to fit? Yeah, it's going to fit. All right, sorry. Yeah, put it against me. Okay, here we go. So we're going to move the coil. Oops, a little bound up here. Sorry. Let's make it look nicer. Okay, and notice the coil is, well, okay, don't do anything for starters. Let's just do this. I hope they can see. I know I'm going to block it for you guys. Oh, yeah, I'm getting some current. And I don't know if you can notice, folks at home, but depending on the direction, I also get a sign in front there. You see that every once in a while? Look right there. What do I get? Especially as I go down. I'm getting, can you see it? A negative sign. Why does that make sense? This is on voltage now. Why am I getting positive direction Liam, go ahead.
Well, it's like also the same thing that we had before, with the smaller scale, or we split the one out.
Yeah. And that negative and positive probably means what about the electrons in this circuit? What do you suppose the negative and positive voltage means about the electrons? About how they're moving? Zach? You got it. So one direction, I don't know which, is positive voltage. Let's say that's when they're pushed. And when they're pulled, it's negative voltage. And I want to see if folks at home can see that as well. Look here for the negative sign when I do this. Okay, now, and you should see every other one is negative. In fact, if you look carefully, when I go down, it's negative. When I go back up, it's positive. Okay, I'm also going to do something else. Okay, this is for everybody. I'm going to go down really slowly. I'm going to go up really slowly. What do you notice about the numbers when I do it like that? What do you notice, Corey? You can't really see it? I'm sorry. Okay, so hard to get this where everybody can see it. What about somebody at home? Okay, thanks, Kiara. You're right on the money. I'm sorry I didn't see that. Okay, Kiara says the slower you go, the less current you produce. Right. So, or I can also say the faster I move this coil, Ingrid, the current I produce.
I can't see it all.
Well, go ahead and stand up. You guys need to see this, okay? So I'm trying to get it so folks at home can see, but you should be able to see too. So I want you to see this thing right there. So move so you can see it. Now I'm going to go slow, Ingrid, just so you can compare. Yeah, okay. So if I move the faster, what is this thing? The coil. So I move the coil faster in the magnetic field, I make more voltage. And if I move it slower, I make less voltage. Good. So you can put that under observation. I'm trying to stay here and point this stuff out at the same time. Observation. What about the explanation? So why? Especially, why do I get negative again going one direction? What did Zach say? Why do I get negative voltage like half the time? So it looks like this every time I'm going down. Nope. This one is up, it looks like. Yeah. Up I get negative now. I must have turned something around. Because what's going on, Tim? Yeah. So why was it again? It looks on here, I said observation and then explanation. So let's explain why I get, first off, negative voltage half the time. What did we say about the electrons, Tim?
Well, I was gonna say that the measurements are not low enough, so. Wait, no, sorry.
You're thinking about the second thing. Let's go to the first thing. So my question, Tim, and everybody is, why do I got negative voltage half the time when I do this? Claire, help out. Okay, good. Good. So they go one direction positive and the other direction, Claire? Then negative. So ready, I'm going to pull this off for a sec. Now look at them. The coils go like this. So the electrons are actually going what? This way or this way? Which I hope makes sense to you. Remember how we talked about being a 90-degree angle? Well, check this out. I'm pushing down like this, and then the electrons are going this way or this way. That's 90 degrees again. We keep hitting these 90-degree angles. And that's what I want to emphasize with some of these labs we do, okay? All right. Folks at home, let me read some of your comments as well. Yeah, exactly, right, Michael, it moves the electrons the other way, that's correct. Yeah, okay, and we'll come to that. Michael, we're gonna come back to your earlier comment about the metal detector in just a moment. That's good. Okay, and Kiara says you get a negative voltage because the electrons go in the negative direction and the other way they go into the positive direction, right as rain. Good. Okay, folks here in the classroom, did we talk about a metal detector yesterday? We didn't talk about a metal detector? Bad teacher. Okay, so I thought we did that. Let's finish this and we'll talk about a metal detector. Thanks, Michael, for reminding me. We'll teach these folks about a metal detector in just a moment. But for now, let's finish up station 1 together. Okay, so I think we did the first part. We moved the coil in the magnetic field. Second thing, we're going to move the field in the coil. Okay, you ready? I'm going to try and hold that up against me so you can see it now. And and again, look at the sign. This time I think when I go in, it's negative. And when I pull out, it's positive. Although I think I'm a little faster than the thing is, so it's a little hard for me to tell, yeah. Okay. And again, if I go real slow, and we'll see what this has to do with the metal detector that Michael mentioned in a little bit. And if I go out, well, so now you can really see it's positive going out, it's negative going in. Okay, so, everybody, including folks at home, what do you call this phenomenon? Well, think of the two effects we have. Which one is this? What do you call this phenomenon, Corey? A generator, okay? So either a generator or the generator effect. That's the name of this phenomenon, right? You got it. Thank you. Exactly, Kiara. Now, here for everybody, including folks at home. In fact, let's do folks at home first for this one. Okay, so you saw me doing several things. Look at the last thing. How can you increase the effect? So we got 4 ways to increase the effect of making voltage. Give me one at least. Can you type in, folks at home? What's one way? You can think here for some of the others. Well, I want at least one way to increase the amount of voltage. What could I do? So you guys type in. There's 4 ways altogether. In fact, maybe I'll put those on the board because that's so important. Okay, so station 1, 4 ways to increase the voltage or the generator effect. Okay, let's see if I got some from folks at home. Oh, I got lots of participation. Good. Okay, Michael is right. He says more coils, but I'm going to leave that for a moment, Michael, because for now, I want to talk about just the 2 movements we did. And Kiara, you're right too, larger magnet. But let's not even do that. Then there's maybe 8 ways, but let's at least do 4 ways. Okay, another thing Michael says is faster movement. But let's be specific. Faster movement, we're going to break it down of what into what. So I guess we get to choose because Michael didn't say. So faster movement of Tim?
Well, if you want to get the generator.
Okay, so faster movement of magnet into coil. What about the coil into the magnet? Did the movement there, Avram? There you go. So same with the other one, Avram. Exactly. So I could do faster movement of, that's the same words, of coil into magnet. It didn't matter, did it? It didn't matter which we moved. So faster movement of the magnet into the coil or the coil into the magnet. Good. Yeah, and Kiara had that as well. And I don't know, high temperature, that probably doesn't help. Michael, it makes more what's called resistance. And although larger magnets would be helpful, I didn't have that in my demo. So something else we could do instead. Okay, so what would I want to say here? Or maybe that is what I want to say. Let me think. How can you increase the effect? Maybe Kiara and Michael, maybe you guys are right. I'm trying to think of folks help me out here. So what other ways could we increase the effect? So we have the amount of movement of either the magnet in the coil or the coil in the magnet. What else could we do? What else could we do? Maybe we do have to change something that's not here, or something that I don't have right in front of me. But Tim, yeah, of what? Okay, so let's take the one Tim just said and Kiara said, and maybe Michael as well. So we could have a greater magnetic field. So increase, so how about use a larger magnet with a greater magnetic field. I'm going to abbreviate that now to mag field. Good. I was thinking of something else, but no, that's exactly right. Okay. Then the other thing I could change here. How about somebody from this group? Whoops. My battery in here is running out. What else could I change in record? You got it. So I could add what? More loops. Okay, so from Core, we can use a coil with more loops. I'm going to be really exact here, Corey, of copper wire. Beautiful. So more loops of copper wire. Let's see if I got anybody else. Moving both at the same time. That really doesn't change it. Reversing the polarity, that makes what's called alternating current, Michael. So it does increase the amount of alternating, but not increase the amount doesn't increase the amount of voltage. But it does make it alternate more often. And your last comment, I don't quite understand, Michael. I'll try that again. Okay, all right, yeah. Okay, good. All right, so let's pause and see if folks here, if you got questions. Okay. Okay. And Irene, you may want to get up and walk around a little bit, take a little fresh air. That will be then just fine. Okay, then, what I would like to do is quickly review with both groups, review with my group at home, do for the first time with you, and talk about a metal detector. Okay, so. Not a bad thing to review for the folks at home anyway, because it's pretty cool. Okay, folks, here, give me a classic place where you have to go through a metal detector. Jake. Airport. Here's the metal detector. Here, let's write it. Metal detector. Here's you. Walking through it, right? Now let's say you have like an iron gun with you. Gun made of steel. Maybe a pistol. Steel is like mostly iron, okay? First off, can you guess now that you've had this class, what do you think you're walking through? What do you think this is? Several hands, Alessia? Exactly. What you're walking through is a big, it's called an electromagnet, but essentially it's a big magnetic field. We're not going to go into how they make that field, but it's essentially a big magnet. So how does this work? You've got some iron on you, right? You've got some iron, and when the iron goes through, what does it make happen? So to speak. Can you guess, Kurt? It's got charges in it because it's made of metal, so it's got electrons in it. And the electrons in it will start to what as soon as you go through the field? The electrons, just like the coil, the electrons will start to move. And when they move, they create another field, magnetic field. And guess what? A voltmeter in this area picks that up. So as soon as you walk through with something metal, you disturb, we could say, the magnetic field here by creating another one. And as soon as you do that, what happens? Yeah, bam, 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 bam. Okay, back up, please. So, when we have metal, we create another magnetic field that disturbs this one. And as Tim said, along. Because it's probably hooked up to a voltmeter. And the voltage changes and suddenly they know somebody's got a piece of metal. Now, yes, exactly. So let's do what Kiara said and what Michael said earlier. What would happen if a person walked through this really slowly? What if they walk through this thing really slowly, Leo?
Would it not be this low?
Yeah, it will again?
It wouldn't be this low.
Yeah, it won't go, the alarm won't go off. Because if I go through slowly enough, what happened with our voltage here? Ben?
It just, it doesn't barely go up.
It barely goes up. If I go really slow, maybe I can make it so I don't. Okay, now I gotta tell you this. Don't try to do that. You think they like it when people do that? You think they're gonna let you do that? No, they're gonna say, okay, you back up, walk through again, normal speed. No, okay. They know that trick. They know that trick because they know the physics. They've been taught about this, okay? People gotta walk through because if they go slow, it doesn't set off the alarm. So you're gonna have to walk through at normal speed. And again, please don't try because if you try, you're gonna be there for hours probably, okay? So,
Or elderly, they don't
okay, if they're elderly,
We get pushed.
yeah, often they're pushed through anyways. And quite often they got a wheelchair and it sets off the alarm anyway. And then they do what? They take them aside and use a,
The probe.
no, it's not a probe. It's called a, starts with a W. A wand. Thank you. Guess what's in that wand? A little tiny magnetic field. And doesn't that make sense now? What are they looking for with that little magnetic field? If they go through an area with metal, then what's going to happen? It's the same thing. So when you have the wand, it's also a magnet as well. So folks at home, did we talk about that? If you have a wand and they do that to you, that's also a magnetic field they're checking you with, looking for metal. Yeah, good. Yeah.
Why do they take the one and like move it so quickly around the ball?
Yeah.
As if they were going slowly with it.
Exactly. If they moved it super slow, we'd have the same non-effect, wouldn't we? And it wouldn't work so well. So they're doing it quick enough. Okay, so they can find wherever your piece of metal might be. Yeah.
How slow do you have to walk though? You have to walk like inhumanly slow to
Yeah. You'd have to walk, Liam, noticeably slow. They're not going to let you do that. Yeah.
Isn't it like you like detectors that like go around like, all around you kind of thing?
Can you guess what's in the part that moves around you? Now that you know some physics, what's moving around you probably, Corey? Exactly.
get dangerous though.
Now, it's a really, really small, how should I say this? It's not an effect that affects any of the biological cells of your body. It just sees if you're carrying any metal. But it's not like it's sending x-rays through you or anything like that. It's not that. It's a magnetic field, and it goes around you to see if you got any, oh, I got to take out my keys. Okay, so then I'm gonna set it off. Okay? Good questions. Any other questions from you or folks at home? Yeah, exactly. Okay. Let's see.
So do you metal detectors like the one that you see in, TV, so they have that desert looking detector also have a little electromagnet in them?
Yeah. So if you've seen metal detectors people carry,
Yeah.
looking for bombs or looking for treasure or whatever, those also have in it. The part that you're moving over must have a magnetic field. And if it moves over a piece of metal that's underground, then of course there's something that's probably got wire in there as well, and the electrons in the wire will then start to move. And its current or voltage will tell the thing, oh, here's metal beneath here. Okay? And we're going to do the same thing, by the way, in another day or two. I'm going to show you that it doesn't have to go through the metal detector to detect it. Sort of like, Stella, if it's below you, like here's my metal detector, right? And even if the metal's here, I can still detect it without going through some sort of NIDA. We'll see that that still changes it enough to feel it, as it were. Yeah.
If the like metal detector is powerful enough that it's emitting enough of a magnetic field, and let's say you have like a landmine or something, could it mess with the landmine?
No, not to my knowledge, because the landmine is set off by a physical pressure of the soil on the actual landmine.
So if you dig it up,
Then that's a problem, because if I dig it up, then I gotta dig it up really carefully, because I don't want to put any pressure on the top of it. So these people that do that really dangerous job are very careful and really know their stuff on how to dig around to carefully take it out. It can be done, but it's not easy. Not easy. Good. The other place you'll see a magnetic field is in front of some stoplights. You'll see like a piece of asphalt that's been replaced, and there's a loop of metal underneath the road. So when a car drives over that loop of metal, it indicates to the traffic light what? That there's
That there's like a car there. So
and what
it-
should the traffic light do? Change to green. It's called a smart light. So it also uses a metal detector. Good. Thanks everybody for joining us at home. Yeah, you keep that and we'll work more on the stations when I see you tomorrow. So we'll see you then. Folks at home, I'll send you an invite, but let's meet again tomorrow, okay? Thanks for joining me. Bye-bye.
Stella, are we in the library?
Bye.